Okay, so today we're going to talk about section 1.2, which covers more about transformations of parent functions, specifically or mostly focusing on absolute value functions. So up at the top, a transformation changes the size, shape, position, or orientation of the graph. So basically any change that we make to the original function. A translation is a transformation that shifts a graph horizontally and or vertically but does not change its size or shape or orientation. So again, translation, we kind of talked about it in 1.1, that's just shifting something left, right, up, or down, just moving it around the graph without actually changing any of the aspects like shape or size. So all of these examples we're going to base off of an absolute value function. We're going to talk about how to make these different transformations. So for a translation, there's two different ways that we can translate something. We can go left or right, or we can go up or down. And if we want to go left or right, that transformation comes by adding or subtracting something inside of the absolute value bars. So my first example is going to be, I'm going to take f of x equals the absolute value of x, and I'm going to translate that 2 units right. I'm just going to write the equation. I'm not going to graph it. So that new function would be g of x equals the absolute value of x, and then how I get my graph to shift left or right is I'm adding or subtracting something inside of the absolute value bars. If I want to shift right, I'm going to do x minus 2 inside the absolute value bars. If I wanted to shift to left, this would be an x plus 2, and we'll talk about that a little bit more in a little bit. If I want to translate up or down, I need to add something outside of the absolute value bars. So if I do a vertical translation, my new function would be g of x equals the absolute value of x, and that's just what my original one was. And then say I want to translate this 3 up. If I want to move it 3 up, I would add 3 to the outside of the absolute value bars. The next type of transformation is a reflection. So when something flips over, usually the x-axis, the y-axis, but just it's called a line of reflection. So if I want to reflect something, I'm going to start with f of x equals the absolute value of x. If I want to reflect that, I need to negate it, basically. So I need to flip all of the signs of my output. So how I do that is we'll call the new function g of x. G of x would have to be not just the absolute value of x, but the negative absolute value of x with that negative sign out in front. That just flips all of your outputs, so it flips everything over the x-axis. The next one is a vertical stretch. That's a transformation where all the y-coordinates are multiplied by the same positive factor other than 1, and where the factor is greater than 1. So it's just any time we're basically pulling something up or extending the y values, making the graph appear, I guess, taller is one way to think of it. So if I start with f of x equals absolute value of x, my new function, I'll start with g of x. And then say I want to stretch that by a factor of 2, by a scale factor of 2, my new function would be 2 times the absolute value of x. So what that would do is that would take all of my y-coordinates and multiply it by that 2, that positive factor. In order for it to be a stretch, though, your factor, that number that's out in front of the absolute value bars, has to be greater than 1. And then for vertical shrink, it's a transformation where all the y-coordinates are multiplied by the same positive factor other than 1, and the factor is greater than 0 and less than 1. So we kind of talked about this in 1.1, but this is anytime you have a factor like a fraction, or a fraction that's less than 1 specifically, or if you see a decimal, which you won't typically see. So if I want to have a vertical shrink, we'll call my new function g of x, and say I want to shrink that function by a scale factor of 1/2. 1/2 would become that number out in front of the absolute value bars, so 1/2 times the absolute value of x. That would be taking my parent function and shrinking it by a scale factor of 1/2. So you may remember a little bit, you may not, it's not that big of a deal. Just kind of like, not a formula, but a little equation from Algebra 1 that helps us put all of these transformations together for absolute value bars. So that function is, or for absolute value function, excuse me, that'd be f of x equals a times the absolute value of x minus h plus k. And this combines all of our possible transformations right here. So this a tells us whether the function has been stretched or shrunk. This h tells us whether the graph has been translated left or right. And this k tells us whether the graph has been shifted up or down. So the value of a, whatever a is, we focus more on the absolute value when we talk about stretch or shrink. And then if a is negative, then our graph is also reflected. So if a is negative, our graph is reflected. And you'll see this, and you'll see the quadratic version of this a lot, this chapter and next chapter also. Okay, so example 2, graph the function and identify its parent function, then describe the transformation. So g of x, or number 1 is g of x equals 2/3 x plus 2. That's just a normal slope-intercept line. It's not anything special. So we graph that by starting with the y-intercept, then using our slope to find our next point. So g of x equals 2/3 x plus 2. So my y-intercept is 2, so that's going to be my first point. And then my slope is 2/3, so to find my second point, I'm going up to right 3. If you want to find a third point, you can go up to right 3 again, or you can go down to left 3 if that helps, if you ran out of space. And then you can connect those points. So because this graph is linear, because it's just a straight line, the parent function is actually just like y equals or f of x equals x. That was in the very beginning of 1.1's lesson. So our parent function is just f of x equals x. So what that is basically this function with all of the different transformations taken off of it. So they're all taken off and we're just left with that x. So I'll graph that in green, just so we can kind of see the comparisons as far as the transformations. So up above we were told that a vertical shrink is when you have a number or a scale factor out in front that's between 0 and 1. So we do have that scale factor. We have a scale factor of 2/3 that's being multiplied by our input x. So that means that we have a vertical shrink by a scale factor of 2/3. So vertical shrink by a factor of 2/3. And then we have one more transformation because we have this 2 added. This plus 2 shifts our graph up. So we also have a translation up 2. And you can kind of see those transformations just by looking at the graph. So if my parent function is the green one, you can see that this green line has been moved up 2, but it's also been flattened out. So it's been shrunk, where it's been kind of like squished so that it's closer to the x-axis. So for number 2, we're going to talk about what the different transformations are first, and then we're going to start to graph it. We kind of talked about up at the top what each different piece of this function does as far as what kind of transformation it creates. So this is what we're going to use in order to kind of decipher number 2. So k of x equals 2 times absolute value of x minus 4 and then minus 1. Up at the top we talked about that if there's a number here that indicates that there is a stretch or a shrink, so vertical stretch or a shrink, because this number is greater than 1, it's a stretch. If that was like a 1/2 in there, 1/3, something between 0 and 1, it would be a shrink. We also talked about if we have a value in here being added or subtracted from x, that means that we are going left or right. We're shifting left or right. It's really important that you notice and you remember that there's already a subtraction sign in here. It is x minus h. That negative or that subtraction sign is embedded in there. So if you see a negative here, that means that h is actually just 4. It's not negative 4, because if I were to substitute a negative 4 in here, that would become x minus negative 4, and that would become x plus 4. So h is 4. Since it's positive 4, that means that we're going right 4. So h tells us left or right. And then if we have a value outside of here, that's our k. So if we look back one more time, there's a plus k up here, and that tells us if there's up or down. So since I have a minus 1 here, that there's no negative automatically embedded at the end there, or a subtraction sign. So this means that k is 1. Sorry, negative 1. And we need to go down 1. And then before we graph this, the parent function, its absolute value, so our parent function is f of x equals the absolute value of x. So I'm going to graph the parent function first in green. So remember, absolute value of x, it starts at 0, 0. You have a point at 1, 1, 2, 2, negative 1, 1, negative 2, 2. And then there's a couple of different ways that we can approach graphing this. So if we just do it based off all the transformations, we'll have to do it in a couple steps. One thing about transformations is you have to be really careful to do them in order. So think order of operations. With order of operations, we always multiply before we add or subtract. So since stretch is a scale factor that we're multiplying by, we have to figure out the stretch first before translating the graph. If we translate first and then use the stretch, you will not end up with the correct points. Okay, so I'm going to use just little x's to show where the points are once we stretch it, and then we'll translate it and get our final graph. So if I'm starting at 0, 0 to stretch something, you just need to take all of the y-coordinates and multiply them by 2. So my y-coordinate here is 0. If I multiply that by 2, it's still 0. For 1, 1, if I multiply my y-coordinate by 2, that point becomes 1, 2. For 2, 2, if I multiply my y-coordinate by 2, that point becomes 2, 4. If our scale factor is 2, we're just doubling the height of the points. We don't change the x values. And then you can either reflect these points over the y-axis, or you can do the same with these 2 points as we did before. So negative 1, 1, if I multiply the y-coordinate by 2, it becomes negative 1, 2. And then negative 2, 2 becomes negative 2, 4. So we've done the stretch. We still have a point at 0, 0. And now we can worry about the translation. So if we're translating right 4 and down 1, you can simply start with these points and just count them off to shift them all left 4, down 1. So if I start at 0, 0 and I go left 4, so 1, 2, 3, 4, and then down 1, this is my new vertex. So you can sit there and you can count off all these points, or you can just kind of see how the points are in relation to each other. From my vertex, I have a point up to and right 1. So from my vertex, I can plot a point up to right 1. And then I have a point, another point up to right 1 from there, so up to right 1. Just important that you pay attention to the relationship between each of the points in order to get an accurate graph. And then from the vertex, I can go up to left 1, and then again up to left 1, and then connect those points. So another way that you may have graphed these absolute value functions in the past, which also works, is you can shift the graph based on like h and k based on where the vertex moves to, and then you can use the stretch as a form of a slope, I guess. So if we look at the parent function, a, or that coefficient out in front, is technically 1, and if we look at our green graph, on the right side of the vertex, our slope is 1, and on the left side our slope is -1. So if we're stretching that function, it really just like changes the slope, basically, for lack of better terms, as far as the absolute value. This doesn't work well, obviously, when we go to quadratics because the slope is not constant. So if I moved my vertex over and then I know that this 2 is stretching my slope upward by a scale factor of 2, you'll notice that on the right side of my new vertex the slope is 2, and then on the left side the slope is -2. It's just a reflection. But you do want to also get comfortable with stretching the points like we did at first, as far as like multiplying the y coordinates by 2 and stuff like that, because that'll help you in the next chapter. And then we already kind of described the transformations, but there's been a stretch by a scale factor of 2, a translation right 4, and a translation down 1. So these next set of problems are meant for you to kind of practice on your own, so feel free to stop the video right now and get that practice in. So whenever you're ready, go ahead and unpause it, and then we'll go through these together. So with number 3, y equals absolute value of x minus 1 plus 2. So this minus 1 right here, that's telling me that I need to go right 1. And then this plus 2 is telling me that I need to go up 2. So at some point you should be getting it down pretty quickly on what each number does. So anything inside the absolute value bars, I'm shifting left or right. Anything added outside, I'm shifting up or down, depending on if it's positive or negative. And then if I had a number out in front here, that would be a stretch. So this graph is not being stretched at all, so it's actually gonna have the same exact shape as the parent function. I put all the parent functions in green just so that we can reference them. And then I'm shifting all of these points right 1 and up 2. So from 0, 0, I'll go right 1, up 2, and then you can either shift all of the points from a parent function, or if you are comfortable knowing the relationship between the points. So what I mean by that is, like, our parent function had like a point at 0, 0, and then I would go up 1, right 1 to get to the next point, up 1, right 1 to get to the next point. We're not stretching this graph, so that relationship will not change. It will still continue to be like up 1, right 1, like the same type of slope and shape as the parent function. So to get my next point from my new vertex, I'm gonna go just up 1, right 1, up 1, right 1 again, and then I'll go up 1, left 1, and up 1, left 1 again. So the shape of this graph for number 3 should not look any different from the parent function of an absolute value. It's just moved to the right 1 and up 2. And then for number 4, g of x equals -1/2 x plus 3. So that is just, it's just linear, so that's probably how you're going to want to graph it, but we will talk about the transformations after. So my slope is -1/2 and my y-intercept is 3. So I'm going to plot a point at 0, 3. And then my slope is -1/2. I'm going down 1, right 2, right? Because rise over run. And then I can get another point 2, down 1, right 2 again, or you can go up 1, left 2. Just always double check that that slope is negative and it's decreasing, so it is. So this graph, the transformations, even though it's not organized like an absolute value, it looks like slightly different because we don't have the absolute value bars. The transformations do work the same way. So this negative out in front, that tells us that we have a reflection. This 1/2 multiplied by the x, that's our scale factor. So that 1/2 tells us that there is a shrink. And then this plus 3 is added just to our output after we multiply by the 1/2 and make it negative. So this plus 3 translates up 3. And you can see if this was our parent function, we reflected it. So it went from increasing to decreasing. Our graph got a little bit flatter, so it got shrunk or compressed. And then it shifted upwards also. And then for number 5, f of x equals -2 times absolute value of x minus 4, minus 1 plus 2. So we'll talk about all the different transformations. This negative out in front tells us that there's going to be a reflection. This 2 tells us that there will be a stretch. Oops. This minus 1 in here, there's already a negative normally embedded in there, so this is just a positive 1. So we're going right 1. And then this plus 4 added after tells us that we need to go up 4. So remember, before you translate, if there's a stretch, you need to stretch first, and then you can translate after. You have to think order of operations. If we were going to substitute something in, we would want to multiply first before we add or subtract. Okay, so from the parent function, I'm going to stretch it and then reflect it, and then we'll translate it. So my first point at 0, 0, remember if you're stretching something, you're multiplying or vertically stretching something, you're multiplying the y coordinates by that value. So I'm going to multiply all of my y coordinates by 2. So when I multiply 0, 0, when I multiply the y coordinate by 2, that stays here. 1, 1, if I multiply the y coordinate by 2, becomes 1, 2. 2, 2 becomes 2, 4. Negative 1, 1 becomes negative 1, 2. Negative 2, 2 becomes negative 2, 4. So we've done the stretch. Now we have to reflect it. So we just are going to take each of these values, or each of these points, and flip them over the x-axis. So 0, 0 stays in the same spot. 1, 2 becomes 1, negative 2. And then 2, 4 becomes 2, negative 4. Negative 1, 2 becomes negative 1, negative 2, and then negative 2, 4 becomes negative 2, negative 4. So that's our stretch and our reflection, and then now we have to translate it. So we're going to shift each of these points, right 1 and then up 4. So if I start with the vertex and I go right 1 and then up 4, that's my new vertex, and I just have to take each of my other points and move them also, or I can pay attention to just what the relationship between all the points is. So if I want to count these off, I can. If I want to go right 1 and then up 4, I'll end up here. Or you can notice that once I did the stretch and the reflect, you have basically a slope of negative 2 on the right side and a slope of positive 2 on the left side. So you can just use that in order to graph it. So for my vertex, I was going down to right 1. So for my new vertex, I'll go down to right 1. And again, you would end up at this same point if you had just counted them off. So like from this point, right 1, up 1, 2, 3, 4, you end up at the same point. And then I need to go just down to right 1 again, down to left 1, down to left 1. And just I can't express it enough that you guys really can graph it however you feel comfortable, as long as you're getting the right points. Again, if you would rather just count these off, shift them all right 1, up 4, you can totally do that. So another way that you may have done it in the past, and you're welcome to do it now, is by kind of viewing it more like a slope. So if I have a negative 2 out in front, that means that my slope along the right side of the vertex is going to be negative 2. So technically I could have shifted the graph or shifted the vertex right 1, up 4 like I did here. And then this slope becomes negative 2, this slope becomes positive 2. If you've never done it that way and that feels a little confusing, just please disregard it. Just make sure that you are getting a little bit comfortable as far as stretching points by multiplying the y coordinate, because that will be really important in upcoming chapters. And then for number 6, so I just have h of x equals 3 times the absolute value of x. So I just have that a, or that coefficient out in front, and that means that we have a stretch. So if we just have to worry about a stretch, we're just taking each of the original y coordinates from the parent function and multiplying them by 3. So I had points at 0, 0, 1, 1, 2, 2, negative 1, 1, and negative 2, 2. I need to multiply each of those y coordinates by 3. So 0, 0, the y coordinate 0, so that if that's multiplied by 3, that stays there. 1, 1, if I multiply the y coordinate by 3, I end up at 1, 3. 2, 2, if I multiply that 2 by 3, I end up at 2, 6. And then you can do the same thing on the left side, or you can reflect these points over because the graph is symmetric. So this, if I wanted to reflect it, this point would go from 1 to the right of the y-axis to 1 to the left, so negative 1, 3, and then negative 2, 6. And then I still have the point at 0, 0. So now we're going to talk about writing transformations with function notation, and function notation is just a universal way of writing these different transformations regardless of the type of function that you're working with. So whether it's linear, absolute value, quadratic, it applies to all of them. So for a horizontal translation, the way you write that in function notation is y equals f of x minus h, and that means to translate something horizontally, we're basically going to add or subtract a value from the input from your x. For a vertical translation, function notation is y equals f of x plus k. What that is saying is you are just, if in order to add something, or sorry, in order to shift something up or down, you have to add a constant after the function. So say I were to evaluate a function for a given input, I would just add that k after, and that would shift my whole graph up or down. For reflections in the x-axis, that means the same thing as reflection over the x-axis. So in order to do that, we have to negate the output. We have to take all of our y values that we get. Say if we made a table and we have to make them all negative or the opposite. So we write that as y equals the negative f of x. That just tells us whatever we evaluate the function at, we'll make it the opposite sign. For reflections in the y-axis or reflections over the y-axis, you negate the input, so y equals f of negative x. And then for vertical stretches and shrinks, you need to multiply the whole function by that scale factor of a. So y equals a times f of x. For reflections in the x-axis and vertical stretches and shrinks, if the function has multiple terms, you do have to distribute that negative or that a into all of the terms of the function. So for example 3, we're going to start with f of x equals 4x minus 9, and we're going to write new functions given the transformations that they want us to do. So for a, write a function g whose graph is a translation 5 units up of the graph of f. So if I want to translate something up or down, I have to add a k value. So g of x is just going to be f of x plus 5, because that's my k value. I have to add that 5 after my f of x. So g of x is equal to f of x, so 4x minus 9, and then plus 5. And then if you're able to simplify, you should. So g of x is equal to 4x. I don't have any like terms with the 4x, so that stays the same. And then negative 9 plus 5 becomes negative 4. And then for write a function h whose graph is a translation 1 unit to the right of the graph of f. So our new function is going to be h of x, and we're translating something to the right. So h of x is going to be f of x, but it's instead of, if we're translating 1 to the right, we have to subtract that 1 from x. So f of x minus 1. So h of x is equal to f of x minus 1. What that means is wherever x is, you're going to write x minus 1 instead of x. So h of x is equal to 4 times x minus 1. Because instead of f of x and 4x, it's f of x minus 1 and 4 of or times x minus 1, and then minus 9. And then from there we need to simplify. So h of x is equal to, I'm going to distribute this 4 in. So 4 times x is 4x. 4 times negative 1 is negative 4, and then minus 9. And then last thing is just to combine the negative 4 and the negative 9. So our final answer is h of x equals 4x. And then negative 4 and negative 9 together is negative 13. And then for C, write a function k whose graph is a reflection in the x-axis of the graph of f. So if we're reflecting in the x-axis, we have to take f of x and make it negative. So k of x is just going to be negative f of x. So k of x equals, instead of negative f of x, it'd be negative times all of f of x. It can't just be negative 4x. You have to put all of f of x in parentheses. So negative times 4x minus 9, and then you do have to distribute that negative in to simplify. So if I distribute that negative in, negative times 4x becomes a negative 4x, and then negative times the negative 9 becomes plus 9. And then last one for this example, write a function m whose graph is a reflection in the y-axis of f. So a reflection in the y-axis, we have to negate the input. So m of x, because our new function is m, is going to be f of negative x, and that just means wherever you see an x, you change it to a negative x. So m of x is equal to, instead of 4x, it becomes 4 times negative x, and then minus 9. And then last thing would just be to simplify this into negative 4x. So m of x equals, instead of 4 times negative x, negative 4x minus 9. For example 4, we're going to now work with an absolute value function. So let f of x equal the absolute value of x minus 1 plus 2. We're going to do a vertical stretch of 5. So our new function, we'll call it g of x, is going to be f of x. Sorry, I forgot the 5. But a vertical stretch of 5, so we're going to multiply 5 times f of x, right? Because if we have a vertical stretch like we wrote up here, we're multiplying that coefficient or that scale factor by the entire function, by f of x. So g of x equals 5 times f of x. So I'm going to take 5 and multiply it by the entire function. So you have to make sure that if you have multiple parts of the function, multiple terms like that, that you put it in parentheses, or else you will not get your final answer correct. So 5 times the absolute value of x minus 1 plus 2. And then you do need to distribute that 5 in. So you'll distribute to the absolute value bars and distribute it to the 2. So the final answer for that one would be g of x equals 5 times the absolute value of x minus 1, and then 5 times 2, so plus 10. And then we have for B a vertical shrink of 1/4. So vertical shrink works the same way, where we have a scale factor out in front of the function. So we'll call this h of x. And since it's a vertical shrink by 1/4, it would be 1/4 times f of x. So h of x is equal to 1/4 times the absolute value of x minus 1 plus 2, all of f of x. and then same thing, we need to distribute that 1/4 in. So h of x is equal to 1/4 times the absolute value of x minus 1. And then 1/4 times 2 would become 2/4 or 1/2. Oops. So h of x equals 1/4 times the absolute value of x minus 1 plus 1/2. For example 5, let f of x equal the absolute value of x. If you're good with these, feel free to pause it and then watch it just to check your answer. So a translation 6 units down followed by a reflection in the x-axis. So remember, if we have a translation 6 units down, that looks like f of x minus 6. And then if I have a reflection in the x-axis, that becomes negative f of x. That's how I get that reflection. But you do have to pay attention to the order that it gives you, and you have to make sure that it follows that order. So if I just wrote, say, negative, I'm going to write it off to the side. This isn't correct though, so don't write it down. If I were to write my function as negative absolute value of x minus 6, that looks like a reflection and a translation 6 units down. However, you have to make sure that it's written in the correct order, or else it'll follow order of operations. So this would technically be a reflection and then a translation. So if I want to make sure that I translate and then reflect, I'm going to take my original function, I'll take, I'll call it g of x, and for my translation, or my transformation, I'll take the absolute value of x and I'll subtract 6 from it to get my translation 6 units down first, and then I can use parentheses or brackets to do the reflection after. So if I put the absolute value of x minus 6 in parentheses or brackets, that does the translation first, and then I need to make that negative after in order to get the reflection, and then from there I need to simplify it. So g of x equals, I'm going to just distribute this negative in, so negative absolute value of x, and then negative times negative 6 becomes plus 6. So you can see these two are not the same thing, so had you just written it like this without the parentheses, it would have been incorrect. And then for b, vertical stretch by a factor of 8 followed by a translation 10 units down. So a vertical stretch is taking a coefficient and multiplying it by f of x, and then translating something down is taking f of x and subtracting 10 after. So because we are doing stretch first and then translation, you don't have to worry about parentheses or anything like that, because order of operations, the multiplication would happen before the subtraction. So my function was f of x equals x. I'm going to call my new function h of x. And if I want to stretch the absolute value of x by a scale factor of 8, that looks like 8 times the absolute value of x. And then if I want to translate 10 units down, it'd be minus 10. So one thing to be careful about when you're writing these equations is if you have a translation left or right, you typically need to write that first. There's some problems where you won't really get into trouble for it, but there's some problems where it does mess you up, just because if you have something inside the absolute value bars, so like x plus something, you would be simplifying that first. So just make sure you pay attention to order of operations there. And then for example 6, you make cards to sell. Your revenue is represented by f of x equals 3x. Your profit is $15 more than 60% of the revenue for x cards. What is your profit for 200 cards? So we'll set up an equation or function g of x that will represent our profit. So our profit is $15 more than 60% of the revenue for x cards. And our revenue for x cards is 3x. So I'm going to start there. So that's our revenue, and then we're basing our profit, we're saying our profit is 60% of the revenue. So we'll say 60% times 3x. And remember, if I'm putting 60% inside the function, I need to change that to a decimal, so 0.6. So 60% of our revenue, and then $15 more than that, so plus 15. And then one more time, our revenue was 3x. Our profit is $15 more than 60% of our revenue. So 60% of our revenue plus 15. So before we evaluate that at 200, we can go ahead and simplify it. So 0.6 times 3x, that would become 1.8x plus 15. And then now that it's simplified, we can evaluate it at 200 cards. So g of 200 is equal to, I'm just going to substitute 200 in for x. So 1.8x, or 1.8 times 200, plus 15. 1.8 times 200 is 360. 360 plus 15. So our profit, g of 200, or our profit for 200 cards, is $375.